For the purpose of multivariate exploratory analysis, we have developed a data visualization method called Normalized Projection Coordinates, or NPC. Similarly to the popular star coordinates method, it defines linear mappings of high-dimensional data onto an observable display through a set of vectors, where each one represents a data variable and a radial axis, and determines the direction in which users would like the variable to increase. In our prototype tool, an embedded data sample is shown as a dot, while the endpoint of a vector is represented by a square that can be dragged around interactively, allowing users to specify different configurations of the vectors that lead to different views of the data. Here we visualize potassium, sodium, and sugar content from a breakfast cereal database. Given a configuration of axis vectors, the plots for NPC and star coordinates are simply related through rotations and scalings, and also translations if they use different data normalization procedures. One of the main disadvantages of star coordinates is the difficulty to recover data values given the plotted information, especially if the data is normalized to lie in the 0-1 interval. We have designed NPC so that users can estimate values more accurately by orthogonally projecting embedded points onto the axis. We can optionally draw the calibrated axis where the labels correspond to non-standardized data values. In NPC, the length of an axis vector represents a unit of its variable. Thus, for standardized data, which we use here, it corresponds to 1 standard deviation. Alternatively, we can show perpendicular lines to the vectors for reference. In this example, the approximate value of sodium content for the marked red dot is about 1.3 standard deviations above the mean, which is represented at the origin. Since the estimates are only approximations to the true values, we can inspect the error we would make if we tried to recover them. In this prototype, the size of the points depends on the customizable function of the estimation error. The size of the red point is still large, meaning that it has been represented well. For the purpose of illustration, we can compare the projected and true values, which are very similar for that point. However, the error for the pink point is large since its attribute values are much lower than the estimates. By manipulating the error function, we can discard points that have not been represented well. Notice how most healthy cereals with high potassium and low sugar and sodium have vanished from the plot. This is useful for decision making where the errors are warning us that the dataset does not contain cereals with that combination of features. We can also inspect the error we are making on each variable. In this example, potassium values are harder to recover than sugar or sodium ones, since its associated error is larger. The error is also related to the length of the axis vectors. In general, variables with shorter vectors are better represented. Here we color the points according to sodium content. Notice the small error for the variable. Since the axis vector is short, the values appear fairly ordered from top to bottom. For sugar, the ordering is still quite good. For carbohydrates, the error increases and the ordering begins to deteriorate. Finally, for potassium, the ordering is poor since the variable has a smaller effect on the plot due to its longer vector. When we increase the length of a vector, the points will spread out in its direction, similarly to star coordinates. However, if the length is large, the variable will have a smaller effect. For instance, as we increase the length of sodium, its error increases, and the initial ordering of values for the variable breaks down. Error information can also be used to detect outliers, where it is useful to choose the size of the points as an increasing function of the error. In this example, Mapo, which is the only hot cereal in the dataset, clearly stands out. NPC can also help cluster analysis. In this example, we use a toy dataset with 6 separated clusters. We can visualize them by choosing different configurations of axis vectors. When they overlap, it is because some are not represented well. Thus, we can also visualize error information to detect these situations. In this plot, only two clusters are represented well. Thus, we should not draw conclusions about distances regarding the other clusters. With MPC, it is possible to reproduce any linear mapping. The next example uses a wine dataset consisting of 3 classes and 13 variables, and computes configurations of axis vectors that lead to LDA, that is, linear discriminant analysis, plots. By iteratively discarding the variable with the longest vector and recomputing LDA, we can reduce the set of variables before the classes begin to overlap, providing clues about which variables are more discriminative. On the first plot, the vector for magnesium was so large that it essentially had no influence on the plot. Therefore, magnesium is very likely the least discriminative variable. Finally, for this dataset, the classes can still be separated using 6 variables. Another useful linear mapping is PCA, that is, principal component analysis, which provides the configuration of axis vectors that leads to plots with the least possible estimation error for an entire dataset. In this case, the vectors point to the same half space, indicating that most correlations will be positive. Finally, we have implemented the prototype in MATLAB and includes other elements for retrieving values, filtering, or zooming and panning. We hope these examples illustrate the benefits of MPC for data analysis.